Hi, I'm Ken the Metal Professor. I am trying to keep myself going on this series of videos I'm calling Today on Math Reddit, where I trawl through the askmath and learnmath subreddits looking for questions that are kind of in that algebra, pre-calculus, calculus zone that can be answered fairly quickly, but might have some interesting facets to them that lead to decent ideas and perhaps further thought. These answers or these questions will certainly have been answered on the subreddit very, very well. So I'm not pretending that I'm giving the answers right off the bat. I'm just trying to frame them with some visuals in case it helps anybody a little bit more. So for today, I've picked 3 problems that involve compound inequalities, logarithms. Well, or I have an extra S, so that must be logarithms as done by snakes. I'm not going to go back and fix that at this point. And a calculus problem involving integration using the power rule, or at least that's what it boils down to. Okay, so the first one I've selected is from the user DryExchange6280 on the r/askmath subreddit. The question as posed came with an image that showed a number line highlighted from -6 to 6. This is not the original image in the post. This is my own quickly cobbled together version of that image. You can ignore the vertical stretch. It's just supposed to be a number line from -6 to 6. And the prompt in this problem was to write an absolute value inequality that describes that region of the number line. So this is a story about starting with a fairly straightforward verbal description of that stretch and tightening the description so that we can make it more and more formal in terms of the math. And you can do this a little bit at a time, which is what I've done here. Right, so in words, if we look at this picture, if you're describing this over the phone to somebody, you just, you know what, I'm looking at the number line between -6 and 6. The set of all values between -6 and 6. And note, we are including -6 and 6 as well. So what do we mean between -6 and 6? Let's make that a little bit more formal. Well, we're looking for the set of all values that are greater than or equal to -6, but also less than or equal to 6, right? If you're on this picture and you're standing at the -6, you're looking uphill towards the values, but over here at 6, you're looking downhill back into those values. So the set of all values that are greater than or equal to 6, but less than or equal to -6. Now, values, right? Usually we give values names. So that we don't have to keep writing the set of all values, let's introduce a generic name for those values and say, well, that's the set of all values that we're going to call X. And those values are greater than or equal to 6, but less than or equal, greater than or equal to -6, but less than or equal to 6. Now that we've introduced the name and these descriptions of greater than and less than, we can tighten that down a lot by saying, hey, we're looking at the set of all values named X that are greater than or equal to -6. And at the same time, those same values are less than or equal to 6. The reason we like and instead of but is because and is a formal logic word. It's a logical operator. And it allows us to conjoin different bits and pieces of math. Now, this X greater than or equal to -6 versus X less than or equal to 6 is kind of apples and oranges because the inequalities are facing opposite directions. If they're in the same direction, we could append these. So that's what we're after. So what we're going to do is take this one on the left and say if X is greater than or equal to -6, that means that -6 is less than or equal to X. And now this X can be like the glue that's then going to stick these two things together, and we can finally squish it all down to saying the set of all values that satisfy this relationship in bright green. Maybe that's not very visible. I'm sorry if it's not. But that is how we would present the mathematical description. The inequality that describes that region is read as -6, less than or equal to X, less than or equal to 6, which if you'd like to unravel it, the best one here to match that is it's the set of all values that are greater than or equal to -6 and also less than or equal to +6. That's it. So in situations like that, if you can describe what you're looking at verbally, go ahead and write it down and then start to just tweak it a little bit at a time by putting in more formal math until you get to the final result. Okay, the next problem is about logarithms. This one was kind of fun because it looks terrible, but it's really a brain twister. So the question was to solve the equation 169 equals 11 raised to the log base x of 169, and we're supposed to solve this for x, which looks awful. There are algebraic steps that you can take to solve that, and people have already shown those in that problem. So you can go look this up, search by the user, and see what those steps are. But I like the story to this just because it's a puzzle which you can unravel just by understanding logarithmic notation. So that's why I'm showing it here, is just some practice with that. It's kind of like a twisted donut of math symbols. It's like math inception. You'll see why. So like I said, you can solve it with algebra, or we just unravel what the statement is telling us. And this is why I liked this problem, because it gives us a chance to review exponential versus logarithmic notation. Okay, each of these modes of notation are a way to relate three values together: a base, an exponent, and a result. Now we're all most used to using exponential form. B to the A equals C, right? This ties together three values. There's a base, there's an exponent, and there's a result that comes about when you take the base and raise it to that exponent. This is the normal setup for these. When we switch over to logarithmic notation, we're still relating these three values just in a different way. The reason we want two modes of putting these values in play is that here, the exponential notation sort of emphasizes, it presents to you the result of taking the base and raising it to an exponent. 3 to the third is equal to, here you go, 27. The base and the power gave us this result. Ta-da! There are scenarios where we have a relationship between these three numbers, a base, an exponent, and the result, and it's actually the exponent that is the most interesting piece of those three values. For example, a pH scale. When you report the pH of a solution, that number comes from an exponent in an expression. Decibel scales, the Richter scale. Whenever you throw around these numbers, you're actually handling exponents out of exponential relationships. And so logarithms are a way to present, say, ta-da, here is an exponent that makes all this information tie together. So the exponential form emphasizes the result. When we twist it around to the logarithmic form, again, the same three quantities, but it hands us the exponent. So here we are, the log base b of c equals a. The way you read this is say, I got a base b, and I got a result c. What was the exponent that made that happen to take the base b and return a result of c? Okay, that's why, for example, log base 10 of 1,000. We have a base of 10, a result of 1,000. What exponent on 10 made that happen? 3, because 10 cubed is 1,000. Log base 4 of 1/16 is -2. Why? Well, when we see log base 4 of 1/16, that represents a number. It represents the exponent that could get put on 4 to return 1/16. Now, to start from 4 and get to 1/16, what do? You're squaring the 4 and you're invoking a reciprocal. So the negative sign is the reciprocal operation with exponents, and 2 is the squaring. So the inverse of 4 squared is 1/16. And similarly, log base 1/2 of 16 equals -4. If we had a base of 1/2 and we got a result of 1/16, what was the exponent that we put on 1/2 to give 16? Here it is, it's -4. So the logarithm emphasizes the exponent that's involved in a base exponent result triple set of numbers. Okay, so back to the problem. 169 equals 11 raised to the log base x of 169. Good grief. Okay, we're not going to do any algebra. We're just going to resolve this understanding logarithmic notation. So let's just focus on the exponent right now of the 11, okay? Log base x of 169. What is that? That represents a value that has been handed to us. There's a base of x and a result of 169. Log base x of 169 says, here you go. This value is the exponent that would go on x to give us 169. Okay? That's a quantity, the power we'd put on a base of x to get 169. That's what this means. Now, we aren't trying to figure out what that power is. Okay, that's not the point of the problem. We're trying to solve for x. We want to know what number would go right there in the base of the logarithm to make this whole thing become true. So we're trying to decide what x is. We have a quantity right here that says this quantity is the exponent we put on the mystery number x to get 169. Now, in this right-hand side, we're taking a base of 11 and raising it to something to get 169. Now put these two things together. We're raising a base of 11 to a quantity that's the power we'd put on some base to get 169. And when we do this, we're getting 169. So what does that mean x is? That means x has to be 11, right? Right? Spinning your head around. We didn't do a lick of algebra. We just understood what this notation means. Now, again, you can go back to this thing and rearrange and manipulate and do some algebra and still end up extracting x equals 11. And you can go back and find this question to see those details if you would like. All right. And then the third question is a calculus problem. I realize I left off in this title of the slide. Sorry there, Speedy Pro YT. This should be Speedy Pro YT, capital Y, capital T. And I know that because A, I thought I typed it earlier, and B, I think I chose one of their questions a couple of videos ago last week. So congratulations on having a second one of yours selected for these things. This was just fun because of the nested roots here. So you're doing an integral of the square root of x times the square root of x times the square root of x. This ends up just being a power rule problem, but easier said than done, right? So let's turn that mess of nested square roots into exponents. And the kicker is to remember that when we multiply with a common base, we add the exponents. When we have nested exponents, we multiply the values. So let's work from the inside out. That interior, x times the square root of x, that's x times x to the 1/2, and that's simple enough. That's just x to the 3/2. Now, let's take this square root of x to the 3/2 and rewrite that as x to the 3/2 raised to the 1/2. Now multiply those exponents. Now we're at x to the 3/4, and we're still waiting to multiply by this last x here. But now we just add those exponents. X times x to the 3/4 becomes x to the 4/4 times x to the 3/4, or x to the 4/4 plus 3/4. So that's x to the 7/4, and that is under a square root, which means we're raising it to the 1/2 power. And so this whole thing shakes out to the antiderivative of x to the 7/8. That was the fun part of this. Now that we're at that point, it's boring, right? That's just a straight power rule. If you know the power rule, you know how to do this. Finding the antiderivative of x to that exponent means we add 1 back to the exponent and multiply by 1 over that new exponent. And then we simplify with some fractions. You get a 1 over 15/8 in the front, and so there's 8/15 times x to the 15/8. So this page was dull. It was this stuff that was the fun part of this problem. So there, 3 problems for today. I hope everybody in the U.S. had a nice extended 3-day weekend. If you're outside of the U.S., I hope you had a good old normal weekend. I will keep up trying to do things like this, if not every single day, hopefully every other day. You can find me at metalprofessor.com and also the Metal Professor YouTube channel, which you've already found that if you're watching this.